Tonight, before sleep finds you, take a slow breath. The day is finished. Whatever was urgent an hour ago can wait a little longer. Settle into wherever you are and let your body feel its own quiet weight again. We are going to drift very slowly into the deep, slow story of our home galaxy, where 200 billion stars have been quietly turning together for nearly 14 billion years. Welcome to the Circadian Institute. Each night we go somewhere far from the noise of the day, somewhere ancient, somewhere unhurried, somewhere ready to receive a tired mind. Tonight that place is the deep, slow story of the Milky Way. Quiet spiral arms threaded with gentle starlight, ancient star clusters older than the Earth itself, patient cosmic dust that drifts between the stars, and at the very center, a vast, quiet black hole that keeps the whole great wheel turning, all moving in their own unhurried ways across deep cosmic time. A subscription is the quiet way to stay with us for tomorrow's journey, and the one after. Let your body settle. Feel the support beneath you. There is nothing you need to do tonight, nothing you need to remember. The Milky Way has been turning quietly for nearly 14 billion years, and tonight is simply one more quiet moment within that vast, patient story. Tonight we drift into the deep, slow story of our home galaxy. Its 200 billion stars, its quiet spiral arms, its ancient globular clusters, its patient cosmic dust, and the great gentle black hole at its center that has kept the whole vast wheel turning for ages beyond imagining, toward a kind of patience measured not in years but in galactic years. The journey is slow on purpose. There is no part of this story that requires you to stay awake. If you fall asleep before we are finished, that is the right ending. Let the bed hold you, and let the patient cosmic story begin. To begin the story of our home galaxy, we have to imagine a structure so large that ordinary human measures of distance are no longer useful. The Milky Way is a vast spiral wheel of stars, dust, and gas, slowly turning together through the depths of space. Tonight we will move through it gently, and there is no hurry at all. If we could pull ourselves far above the disk of the galaxy and look down at it from a quiet vantage point, the Milky Way would appear as a slow-turning spiral with several long, graceful arms winding outward from a bright central region. The disk is wide and thin, like a great quiet plate of light suspended in the dark. From edge to edge, the Milky Way is about 100,000 light-years across. A light-year is the distance that light travels in 1 year, and light is the fastest thing in the universe. So when astronomers say the Milky Way is 100,000 light-years across, they mean that even light itself takes 100,000 years to cross from one side of our galaxy to the other. This is a number that is difficult to feel in any ordinary way. 100,000 years is longer than all of recorded human history. 100,000 years ago, the first modern humans were still leaving Africa, and yet that span of time is only the time it takes a single ray of light to cross our home galaxy from one edge to the other. The Milky Way contains roughly 200 billion stars. The exact number is hard to pin down because many of the smallest, faintest stars are difficult to count, but 200 billion is a reasonable estimate. If you tried to count them at 1 star per second, it would take you about 6,300 years just to finish counting. These 200 billion stars are not packed close together. The galaxy is mostly empty space. The stars are separated by enormous distances, typically several light years between one star and its nearest neighbor. From the perspective of a single star, the rest of the galaxy looks dark, with only a few small bright pinpricks scattered across the night sky. And yet, despite all that emptiness, the Milky Way contains a remarkable amount of material. Beyond the stars themselves, the galaxy holds vast clouds of cold gas, drifting nebulae of warm gas, fine cosmic dust scattered throughout the disk, and ancient remnants of stars that died long ago. All of this is bound together by gravity, and all of it is slowly turning around the center of the galaxy. The shape of the Milky Way, when seen edge-on, is a thin disk with a central bulge. The disk is about 1,000 light-years thick, which sounds like a lot, but it is only 1% of the disk's diameter, so the Milky Way is, by ratio, much thinner than a sheet of paper. It is a wide, flat, gracefully turning structure suspended in deeper space. Around this main disk, our galaxy is surrounded by a much larger and much fainter structure called the galactic halo. The halo is a roughly spherical region containing very old stars, ancient globular clusters, and a great deal of mysterious dark matter that we cannot see directly, but whose presence we can feel through its gravity. Astronomers think the Milky Way formed about 13 billion years ago, only about 800 million years after the Big Bang itself. Our galaxy is among the oldest and largest spirals in our cosmic neighborhood. It has been quietly turning through space for nearly the entire age of the observable universe. In the time since then, the Milky Way has slowly grown by absorbing many smaller galaxies and gas clouds that drifted too close. We can still see traces of these ancient mergers in the patterns of stars in the galactic halo. The Milky Way of today is the patient sum of countless quiet collisions across deep time. Among the largest spiral galaxies in the local universe, the Milky Way is fairly typical. Some galaxies are a little larger, some a little smaller, but the basic structure, a thin disk with spiral arms, a central bulge, a surrounding halo, and a central black hole, is shared by many of our cosmic neighbors. Our home galaxy is not unusual, it is simply ours. The Milky Way is also our home in a very direct way. Every star you have ever seen with your unaided eye on a clear night is a star within the Milky Way. The sun, the planets, the Earth, the moon, every familiar point of light in the sky, all of them are within this one quiet galaxy. Tonight we are inside the story we are telling. From inside the Milky Way, looking outward, we see our galaxy as a faint band of light stretching across the night sky on a dark, clear night. That gentle, hazy band is the combined glow of countless stars in the disk of our galaxy, seen from the inside. Ancient peoples gave it many names: the path of milk, the road of stars, the river of the sky. The name we use today, Milky Way, comes from an ancient Greek myth. The Greeks said that the goddess Hera once spilled milk across the heavens, and the bright trail of that spilled milk became the band of light we still see in the sky each clear night. Many cultures across the world have given the Milky Way poetic names, but the Greek name is the one we still use in English. In Latin, the same myth gave the galaxy the name Via Lactea, the Milky Road. From this Latin name comes our modern scientific term, galaxy itself, which originally meant the Milky One. Every time we say the word galaxy, we are still echoing that ancient Greek name for the band of light across the night sky. Tonight, this old beautiful galaxy is what we will explore. We will move through its quiet spiral arms, visit its ancient stellar nurseries, look in on its central black hole, drift through its vast halo of dark matter, and finally consider the slow approach of our distant cosmic neighbor, the Andromeda Galaxy, with which the Milky Way is destined to merge several billion years from now. There is no need to remember any of this. The journey itself is the point. The names of stars, the numbers of light years, the ages of clusters, they are simply small details in a vast, quiet cosmic story. What matters tonight is the slow, patient rhythm of the words and the quiet drift of your own breath toward sleep. Let us take a slow breath together and gently begin our tour of the Milky Way's spiral arms. Let us drift very slowly toward the next quiet region of our home galaxy. The Milky Way contains roughly 200 billion stars. Each one is a vast hot ball of gas, mostly hydrogen and helium, held together by gravity and warmed from within by the slow, steady fusion of one element into another. Each star is its own small private sun, shining patiently across the dark. Most of the stars in the Milky Way are smaller and cooler than our sun. The most common kind of star is the red dwarf, a small dim star that burns its fuel very slowly and lives for trillions of years. Red dwarfs make up perhaps 3/4 of all the stars in our galaxy. A red dwarf is so small and so quiet that almost none of them can be seen with the unaided eye, even though they are everywhere. The bright stars we recognize in the night sky are almost all larger, hotter, and rarer. The countless faint red dwarfs that fill the galaxy go mostly unnoticed. Stars like our Sun, called yellow dwarfs, are less common but still numerous. Our Sun has been quietly fusing hydrogen into helium in its core for about 4.5 billion years. It will continue to do so for another 5 billion years before it begins the slow journey toward the end of its life. Stars more massive than the Sun are rarer still. Blue giants, hot massive stars, several times the Sun's size, burn through their fuel much faster than smaller stars. A blue giant might live for only a few million years before it exhausts its fuel and ends its life in a dramatic but quiet supernova. The very most massive stars, sometimes called hypergiants, are extraordinarily rare. There may be only a few hundred true hypergiants in the entire Milky Way. These stars can be 100 times the mass of the Sun, but they live for only a few 100,000 years before they collapse, releasing more light in a single moment than billions of ordinary suns combined. Most stars in the Milky Way are not alone. They live in pairs called binary systems or in small groups, where two or more stars orbit a common center of gravity. Our Sun is somewhat unusual in being a solitary star. Most of the Sun's neighbors are part of double or triple systems. Among the binary systems are some of the most beautiful sights in the galaxy. Two stars of different colors orbiting each other, one warm orange and one cool blue perhaps, can produce a slow, patient dance of mingled light visible through a telescope from very far away. These are some of the quiet treasures of the Milky Way. Some stars are very young, only a few million years old, glowing fiercely and surrounded still by the remnants of the gas cloud from which they formed. Others are very old, many billions of years old, having quietly fused their fuel for almost the entire age of the universe. The oldest stars in the Milky Way are over 13 billion years old. They formed shortly after the Big Bang in the very early universe, when the first generations of stars were lighting up the cosmic darkness for the first time. These ancient stars are scattered through the galactic halo and in the most ancient globular clusters. Stars are not simply lights in the sky. They are also slowly making the elements that everything else in the universe is built from. Inside a star, hydrogen fuses into helium. In larger stars, helium fuses into carbon, carbon into oxygen, oxygen into neon, all the way up to iron. When a massive star explodes at the end of its life, it scatters these elements across space. The carbon in your bones, the oxygen in your breath, the iron in your blood, the gold in your jewelry, all of these elements were made inside stars long ago. The atoms in your body have all spent time inside the cores of distant stars before being scattered into space and eventually gathered into the cloud that became our solar system. The Sun itself is what astronomers call a third-generation star. It was formed from the gas and dust of older stars that lived and died long before the Sun ignited. Without those earlier stellar generations, the heavier elements that make up the Earth and everything on it would never have existed. New stars are still being formed in the Milky Way today, at a rate of about 1 or 2 new stars per year. They are born inside the great cool clouds of gas and dust that fill the spaces between existing stars, slowly collapsing under their own gravity into new bright points of light. So our home galaxy is, in a real sense, still alive. New stars are being born, old stars are dying, elements are being made and scattered. The slow rhythms of stellar life and death continue tonight, exactly as they have for billions of years. If we could speed up time enormously, we could watch the Milky Way as a slowly breathing thing. Gas clouds drifting and collapsing, new stars igniting in soft puffs of light, old stars swelling and fading and gently exploding, the whole great wheel slowly turning all the while. That is the deep, slow story of our galaxy across billions of years. Tonight, in countless places across the galaxy, new stars are quietly forming. In other places, old stars are slowly dying. The light from many of these distant events is still traveling toward us and will not arrive for thousands or even millions of years. The Milky Way is full of slow, patient news from far away. If you look up at a star tonight, you are not seeing it as it is right now. You are seeing it as it was when its light began its journey, perhaps a few years ago for the nearest stars, perhaps thousands of years ago for distant stars. To look at a star is to look gently into the past. So when you imagine the 200 billion stars of the Milky Way tonight, imagine them not as fixed lights, but as slow, patient lives, each with its own beginning, its own middle, and its own quiet ending. The galaxy is the long, slow biography of all those stars, written in light across billions of years. Let us drift very gently toward the very center of the Milky Way, where the great quiet galactic core has been turning for nearly 14 billion years. the very heart of the Milky Way, hidden behind thick clouds of dust and an immense crowd of stars, sits the Galactic Center. From our position out in the disk, we cannot see the center with ordinary visible light. The dust between us and the core is too thick, but astronomers have learned to look through the dust using infrared telescopes and radio waves. When we look toward the Galactic Center, we are looking through about 26,000 light years of intervening space, dust, and stars. The light we eventually see has been traveling for 26,000 years. It left the center long before any human civilization existed and arrives at our telescopes tonight. The center of the Milky Way is enormously crowded with stars. In the central region, stars are packed perhaps 1,000,000 times more densely than in the quiet neighborhood around the Sun. If you could stand on a planet near the Galactic Center, the night sky would be filled with brilliant stars from horizon to horizon, with no patches of true dark. Within this crowded central region sits something even more remarkable. At the very heart of the Milky Way is a vast, quiet object that astronomers call Sagittarius A star, often written as Sagittarius A asterisk. It is a supermassive black hole. Around it, the entire galaxy slowly turns. Sagittarius A is about 4 million times the mass of our Sun. All of that mass is packed into a region of space smaller than the orbit of Mercury around the Sun. The density is so high that nothing, not even light, can escape from within its event horizon. From outside, all we can see is the slow influence its enormous gravity has on everything nearby. Astronomers have watched stars near the black hole for many years. They orbit it on slow elliptical paths, exactly as planets orbit the Sun. By measuring those orbits, scientists have been able to weigh the black hole and confirm that something with the mass of 4 million suns must lie at the heart of our galaxy. Some of these stars near the center, called the S stars, complete an entire orbit around the black hole in only a few decades. The closest of them, called S2, swings as close as 17 light hours from the black hole at its nearest approach, moving at perhaps 2% the speed of light. From our distant vantage, this is a slow, gentle drift. From up close, it is unimaginably fast. In 2020, the Nobel Prize in Physics was awarded for the discovery of this supermassive black hole at the center of our galaxy. Decades of patient observation, watching individual stars trace out their slow orbits, gave astronomers the proof they needed. The black hole had been suspected for a long time. Now it was confirmed. In 2022, astronomers using the Event Horizon Telescope released the first direct image of Sagittarius A. The image showed a glowing ring of hot gas around a dark central shadow, exactly the shape predicted by the theory of black holes. After decades of patient indirect observation, here at last was a portrait of the heart of our galaxy. The black hole at the center of the Milky Way is, by black hole standards, fairly quiet. It is not actively pulling in large amounts of matter. The ring of gas around it glows softly, but not violently. Some other galaxies have central black holes that are eating large amounts of gas and producing enormous jets of light. Ours is a more peaceful, more patient cosmic anchor. Even so, when small clouds of gas occasionally drift too close to Sagittarius A, They can be torn apart by tidal forces and slowly accreted onto the disk of hot gas around the black hole. These quiet feedings produce small flares of energy that astronomers can detect. The black hole eats slowly in small, careful meals, separated by long intervals of quiet. Around the central black hole and the dense crowd of central stars sits a structure called the galactic bar. This is a slightly elongated central region, several thousand light-years long, where stars are packed in a long, narrow arrangement rather than a perfect sphere. Many spiral galaxies have such a bar at their centers. Beyond the bar, in the wider central bulge, we find some of the oldest stars in the galaxy. The bulge formed early in the Milky Way's history, when the universe was younger and gas clouds were collapsing rapidly. The stars there are mostly very ancient. They have been quietly fusing their fuel for 10 billion years or more. Among the stars near the Galactic Center are some red giants, old stars in the late stages of their lives, having swelled to enormous size as their cores ran out of hydrogen. These red giants drift slowly through the dense central crowd, glowing with a warm, patient red light visible in infrared images of the core. There are also remnants of stars near the center, neutron stars and stellar mass black holes scattered through the crowd, the corpses of massive stars that died long ago. These small, dense remnants drift quietly through the central region, occasionally gravitating around each other or around Sagittarius A in slow, patient orbits. If you could somehow stand inside the central region of the Milky Way, the brightest object in the sky by far would not be Sagittarius A itself. The black hole is dark. Only the gas around it glows. The brightest sights would be the countless brilliant stars all around you, painting the entire sky with patient, warm light. From our distant earthly vantage, the galactic center appears in the constellation Sagittarius, the Archer. On dark summer nights, looking toward Sagittarius is looking directly toward the heart of our galaxy. The bright cloud of stars and dust visible in that direction is the gentle light of the central bulge, 26,000 light-years away. In some ancient cultures, the direction of the galactic center was considered especially sacred. Ancient Mayans built temples that aligned with the position of the galactic center on certain nights of the year. They did not know about the black hole, but they sensed something important about that part of the sky. Tonight, the great quiet center of the Milky Way is still where it has been for billions of years. Sagittarius A is still there, slowly turning. The dense crowd of stars is still there, slowly orbiting. The dust and gas is still there, slowly drifting. Our entire galaxy continues its patient turning around that ancient cosmic anchor. Let us drift very gently outward from the galactic center toward the long, graceful spiral arms of the Milky Way. Beyond the central bulge of the Milky Way, the disk of the galaxy extends outward in a series of long, graceful spiral arms. These arms wind out from the center like the arms of a slow-turning pinwheel, traced by bright young stars and glowing nebulae. Tonight we will drift quietly through them. Astronomers think the Milky Way has 4 major spiral arms and several smaller ones. The 4 main arms are called Perseus, Sagittarius, Centaurus, and the outer arm. Together they form the long, graceful structure of the galactic disk. Between them lie quieter regions of the galaxy, with fewer young stars and dimmer light. Our Sun does not live in any of the four main arms. Instead, it sits in a smaller secondary arm called the Orion Cygnus arm, sometimes simply called the Orion Spur. This smaller arm is a kind of bridge between the larger Sagittarius and Perseus arms, a quieter side road in the galactic structure. The spiral arms are not solid structures. They are not made of fixed groups of stars. Instead, they are slow waves of higher density that move through the galactic disk, gathering stars and gas as they pass through and leaving them behind as they move on. The pattern of arms is real, but the stars inside them are constantly changing. Imagine a slow-moving traffic jam on a long, quiet highway. Cars enter the jam, slow down for a while, and then exit it at the front, while new cars enter at the back. The jam itself remains in roughly the same place on the highway, but the cars passing through it are always changing. The spiral arms work in a similar way. Within the spiral arms, the higher density makes it more likely for gas clouds to collapse and form new stars. So the arms are bright with the light of recently born stars, hot blue giants, cooler yellow stars, and the great pink emission nebulae that surround them. The arms glow brighter than the spaces between them. Between the spiral arms, in regions called inter-arm gaps, the galaxy is quieter. There are still stars there, but they tend to be older and dimmer. There is less new star formation. The contrast between the bright arms and the dimmer gaps is what gives the Milky Way its characteristic spiral shape when seen from far away. Each of the major spiral arms of the Milky Way has its own quiet character. The Perseus arm, the great outer arm closest to us, is a long, graceful sweep filled with bright stars and visible from Earth on dark nights as the brightest section of the Milky Way's band of light. The Sagittarius arm, lying inward of the Sun, is densely populated with stellar nurseries and old red stars near the central regions of the galaxy. When we look toward the constellation Sagittarius, we are looking through that inward arm and on toward the bulge beyond. The Centaurus arm, also known as the Scutum Centaurus arm, is one of the two main arms believed to anchor the spiral structure of the Milky Way. It carries a great population of stars, dust clouds, and emission nebulae across thousands of light years of the inner disk. The outer arm, far beyond the Perseus arm, marks the gentle boundary between the densely populated inner disk and the more sparsely populated outer regions of the Milky Way. Beyond the outer arm, the galactic disk slowly fades into the deeper darkness of intergalactic space. In addition to the major arms, the galaxy contains smaller features called spurs, like our Orion Cygnus arm. These spurs are shorter, less complete spiral structures that run along beside or between the main arms. They contain their own quiet populations of stars, including our own Sun and its neighbors. Within the Orion Cygnus arm, the Sun is currently passing through a region called the local bubble, a relatively quiet area of low gas density carved out long ago by ancient supernova explosions. The Sun has been drifting through this local bubble for the last few million years, and we will continue passing through it for some time yet. The spiral arms of the Milky Way are slowly rotating along with the rest of the galaxy, but they rotate at their own pattern speed, somewhat slower than the stars themselves. Over hundreds of millions of years, individual stars drift slowly in and out of the spiral arms, while the arms themselves persist as long-lived patterns in the disk. From inside the Milky Way, we cannot see the full spiral structure directly. Our view is obscured by dust and by the very fact that we are within the disk. Instead, astronomers piece together the structure of our home galaxy by carefully measuring the positions and motions of nearby stars and gas clouds. In recent years, the European Space Agency's Gaia satellite has dramatically improved our map of the Milky Way's spiral arms. Gaia has measured the precise positions and movements of nearly 2 billion stars, allowing scientists to reconstruct the structure of our galaxy with unprecedented detail. Thanks to Gaia and other observations, we now know that the Milky Way's spiral structure is more complex than once thought. Some arms are longer than others. Some arms split into multiple branches. The patterns are graceful but irregular, like the slow eddies of a great cosmic river. Some other galaxies have much more dramatic spiral structures than the Milky Way. The famous Whirlpool Galaxy, for example, has two long, graceful spiral arms that sweep around its center like the curling waves of an ocean storm. Our galaxy's arms are subtler, more loosely wound. The Milky Way is what astronomers call a barred spiral with intermediate arm definition. Tonight, somewhere in the galaxy, gas clouds are entering a spiral arm and beginning the slow gravitational collapse that will eventually form new stars. Other stars are leaving the arms and drifting back into quieter interarm regions. The slow, patient choreography of spiral structure continues as it has for billions of years. Let us drift very gently into the great quiet stellar nurseries where new stars are slowly forming inside the spiral arms. Stars are not eternal. Each star in the Milky Way has a beginning, a middle, and an ending. Tonight, in this chapter, we will visit the slow, gentle places where new stars are still being born, the great quiet nebulae that fill some of the most beautiful regions of our galaxy. A nebula is a vast cloud of gas and dust drifting through interstellar space. Some nebulae are warm and glowing, lit from within by the energy of nearby stars. Others are cold and dark, visible only as silhouettes against brighter backgrounds. The Milky Way contains thousands of nebulae of many different kinds. The most familiar nebulae are the bright pink emission nebulae, vast clouds of glowing hydrogen gas heated by the energy of young hot stars within them. The Orion Nebula is the most famous example. It is visible from Earth as a faint smudge of light just below the three stars of Orion's belt. Inside the Orion Nebula, hundreds of new stars are slowly forming right now. The cloud is about 1,300 light-years from Earth, large enough to span 24 light-years across. The light we see from it tonight has been traveling for 1,300 years before reaching our telescopes. Stars begin their lives inside the dense cores of these nebulae. A small region of cold gas slowly collapses under its own gravity, growing denser and warmer at the center as it shrinks. Eventually, the core becomes hot enough to ignite nuclear fusion, and a new star is born, quietly, almost without fanfare. The collapse is not fast. It can take hundreds of thousands of years for a gas cloud to collapse fully into a new star. During that long, slow process, the protostar, the not yet fully formed star, gathers more material from the surrounding cloud, growing slowly heavier and slowly hotter. Around many young stars, the leftover gas and dust forms a slowly turning disk called a protoplanetary disk. Within these disks, smaller chunks of dust slowly clump together to form planets. Our own solar system formed in just such a disk around the young sun 4.5 billion years ago. Some young stars are surrounded by what astronomers call jets, narrow streams of gas being thrown out perpendicular to the spinning disk. These jets are visible as glowing structures pointing away from the young star, like the gentle exhaust of a slowly rotating cosmic engine. Stars rarely form alone. Most stars are born in groups, sharing the same gas cloud and the same brief stretch of time. These groups, called open clusters, contain dozens or hundreds of new stars all about the same age. Over hundreds of millions of years, the stars of an open cluster slowly drift apart and disperse into the wider galaxy. The Pleiades cluster, easily visible in the northern winter sky, is a familiar example of an open cluster. The Pleiades contains several hundred young hot stars, all about 100 million years old. Many of them are still surrounded by faint blue reflection nebulae, the remnants of the gas cloud that gave them birth. Among the great stellar nurseries of the Milky Way, the most famous and beautiful is the Pillars of Creation, a region within the larger Eagle Nebula. Here, towering columns of cold gas and dust stand against a glowing background, slowly being eroded by the radiation of young hot stars within and around them. Within the pillars of the Eagle Nebula, new stars are slowly forming in the cool, dark interiors. As the radiation from young hot stars erodes the outer surfaces of the pillars, the dense cores within slowly collapse to form new stars of their own. The pillars are both birthplace and slow tombstone for the cloud that produced them. The Carina Nebula in the southern sky is another great stellar nursery, even larger than Orion or the Eagle. Carina contains some of the most massive stars known in our galaxy, including the supermassive Eta Carinae, a star perhaps 100 times the mass of the Sun, glowing with the brightness of millions of suns combined. Eta Carinae itself is one of the most extraordinary objects in the Milky Way. It is so massive and so bright that it is constantly shedding outer layers of gas in slow, gentle eruptions. In the 1840s, Eta Carinae brightened dramatically, becoming briefly the second brightest star in the night sky. Today it has dimmed again, but it continues its slow, patient cosmic drama. Some nebulae are dark rather than glowing. Dark nebulae are clouds of cold gas and dust, so thick that they block the light of stars behind them. They appear as silent black silhouettes against the bright stellar background. The Horsehead Nebula in Orion is one of the most famous examples, a dark cloud shaped like a horse's head drifting quietly through space. Inside dark nebulae, cold gas and dust slowly collapse to form new stars hidden from view. Astronomers must use infrared telescopes to peer through the dust and see what is happening within. Many young stars are forming inside the great dark cloud of Barnard 68, for example, hidden from ordinary visible light by their thick natal cloak. The total amount of star formation in the Milky Way today is much lower than it was in the early universe. Several billion years ago, our galaxy was forming new stars at perhaps 10 times the present rate. Today, only 1 or 2 new stars per year are born across the entire Milky Way. The galaxy is slowly running out of free gas to make new stars. Eventually, perhaps 100 billion years from now, the Milky Way will run out of cold gas entirely. No new stars will form. The existing stars will slowly age and die. The galaxy will become darker and quieter, with only the very long-lived red dwarfs continuing to shine. But that ending is far in the future. Tonight, the Milky Way is still a vibrant nursery. Tonight, in countless quiet places across our galaxy, new stars are forming at this very moment. Inside dark dust clouds, inside glowing pink nebulae, inside the slow-turning protoplanetary disks of newborn stars, the cosmic story of stellar birth continues peacefully, exactly as it has for billions of years. Let us drift very gently toward the slow, patient endings of stars, toward the long, quiet stories of how stars eventually grow old and die. Every star in the Milky Way will eventually run out of fuel. The way a star ends its life depends mostly on how massive it was when it was born. Tonight, in this chapter, we will move slowly through the various quiet endings that await the stars of our galaxy. Small stars, the red dwarfs that make up most of the galaxy, live extraordinarily long lives. A small red dwarf can fuse its hydrogen for over 1 trillion years before it runs out of fuel. The universe today is only 14 billion years old. No red dwarf has ever yet died of old age anywhere in the entire universe. Eventually, in the very far future, red dwarfs will slowly cool and fade into objects called black dwarfs, cold, dark balls of dense matter, no longer producing energy, slowly drifting through the dark. But the first black dwarf will not appear in the universe for trillions of years yet tonight. The red dwarfs all still shine. Stars like our Sun, called yellow dwarfs, live for about 10 billion years. The Sun is currently about 4.5 billion years old, so it is roughly halfway through its long, stable, hydrogen-fusing life. 5 billion more years from now, the Sun will begin its slow transition toward the end of its life. When a Sun-like star runs out of hydrogen in its core, it begins to swell. The outer layers expand and cool while the core contracts and grows hotter. Slowly, over hundreds of millions of years, the star transforms into a red giant, a vast, cool, puffed-up star, perhaps 100 times wider than it was before. In about 5 billion years, the Sun will swell into a red giant. Its outer layers will reach out toward the orbit of Mercury and possibly Venus. The Earth itself will likely escape being swallowed, but the surface of our planet will be heated to extraordinary temperatures. The familiar oceans and continents will be unrecognizable. After spending several 100 million years as a red giant, a Sun-like star eventually exhausts its remaining nuclear fuel. The outer layers are gently shed in a series of slow expanding shells of glowing gas. These shells, illuminated by the hot inner core of the dying star, form what astronomers call a planetary nebula. Planetary nebulae are some of the most beautiful objects in the Milky Way. They have nothing to do with planets. The name is a historical accident, given when early astronomers thought their round shapes resembled the disks of planets. Instead, they are the slow, gentle exhalations of dying stars, drifting outward across thousands of years. The Ring Nebula in the constellation Lyra, the Cat's Eye Nebula in Draco, the Helix Nebula in Aquarius. These are some of the most famous planetary nebulae visible from Earth. Each was once a star, much like our Sun, slowly returning its outer layers to the interstellar medium across thousands of patient years. After the planetary nebula has drifted away, the bare core of the dying star is left behind, a small, extraordinarily dense object called a white dwarf. A white dwarf is roughly the size of the Earth, but it contains the mass of about half a sun. A teaspoon of white dwarf material would weigh several tons. White dwarfs no longer fuse any nuclear fuel. They simply cool slowly across billions of years, fading from bright hot white into dim orange, and finally into faint dark red. Eventually, after vast spans of time, they will become cool black dwarfs, invisible cinders drifting quietly through space. Massive stars die in a much more dramatic way. A star several times the mass of the Sun will live for only a few 100 million years before it exhausts its nuclear fuel. As the core runs out of options for fusion, it suddenly collapses inward, and the outer layers rebound off the dense core in an enormous explosion called a supernova. A supernova can briefly outshine an entire galaxy. For a few weeks or months, a single dying star produces more light than billions of ordinary stars combined. Then it slowly fades, leaving behind an expanding cloud of gas called a supernova remnant, scattered with newly created elements forged in the explosion itself. The Crab Nebula in Taurus is the most famous supernova remnant in our galaxy. It was created by a supernova explosion that Chinese astronomers observed and recorded in the year 1054, almost 1,000 years ago. Tonight, its expanding gas cloud is still slowly drifting outward, glowing softly across 6 light-years. After a supernova, the very core of the massive star is left behind. If the original star was not too massive, the core forms a neutron star, a tiny, extraordinarily dense object only about 20 kilometers across, but containing the mass of more than the Sun. A teaspoon of neutron star material would weigh as much as a mountain. Some neutron stars rotate rapidly and emit narrow beams of radio waves from their poles. As the neutron star spins, these beams sweep across the universe like the light of a cosmic lighthouse. From Earth, we see them as regular pulses of radio energy and call them pulsars. The first pulsar was discovered in 1967. Some pulsars rotate hundreds of times per second. The fastest known pulsar spins at about 716 rotations per second, faster than a kitchen blender. And yet, despite this dizzying speed, the pulsar is held together by gravity so strong that no part of it ever flies apart. The contrast between extreme motion and extreme stillness is one of the strange beauties of dying stars. If the original star was extremely massive, more than about 20 times the mass of the Sun, Its core collapse goes even further than a neutron star. The core collapses entirely into a singularity, surrounded by an event horizon, becoming a stellar mass black hole. Such black holes are scattered throughout the disk of the Milky Way, mostly hidden in the dark. Astronomers estimate that the Milky Way contains perhaps 100 million stellar mass black holes, the silent remnants of long-dead massive stars. Most of them are isolated, quiet, and difficult to detect. Only a few are part of binary systems where they pull material from a companion star, producing observable X-ray light. Tonight, somewhere in the Milky Way, a star is going supernova. Somewhere else, a star is gently shedding its outer layers as a planetary nebula. Somewhere, a tiny white dwarf is slowly cooling. Somewhere, a pulsar is sweeping its beams across the cosmos. The slow, patient endings of stars continue peacefully as they have for billions of years. Let us drift very gently outward from the disk of the Milky Way into the great quiet halo that surrounds it. Beyond the bright disk of the Milky Way, in a vast, roughly spherical region surrounding the entire galaxy, lies the galactic halo. The halo extends much further than the disk itself, perhaps 200,000 light-years in every direction from the center. Tonight, we will drift slowly out into that vast, quiet region. The halo is much sparser than the disk. There are stars there, but they are widely scattered, drifting in slow individual orbits that take them far above and below the plane of the galaxy. These halo stars are ancient. Most of them are over 10 billion years old, among the oldest stars in our galaxy. Halo stars are also chemically poor. They formed in the early universe, when only hydrogen and helium were widely available. The heavier elements that we take for granted in our own bodies, carbon, oxygen, iron, had not yet been made by earlier generations of stars in significant amounts. Halo stars are thus living fossils from the early Milky Way. The halo also contains the most ancient stellar groupings in the galaxy, the globular clusters, which we will visit in detail in the next chapter. For now, picture them as small, dense balls of very old stars scattered through the galactic halo, each a self-contained museum of the early universe. But the halo is not made only of old stars and ancient clusters. It is also filled with something far more abundant and far more mysterious: dark matter. Dark matter is a kind of substance that does not emit, absorb, or reflect light. We cannot see it directly with any telescope, but we know it is there because of the gravity it exerts on visible matter. In fact, dark matter is the dominant form of matter in the Milky Way and in the universe as a whole. The visible stars, gas, and dust make up only about 10 to 15% of the total mass of our galaxy. The remaining 85 to 90% is dark matter, scattered through the halo and threading even into the disk itself. Astronomers first realized that dark matter must exist in the 1930s, when an astronomer named Fritz Zwicky studied the motions of galaxies in clusters. He noticed that the galaxies were moving so quickly that the visible mass alone could not explain how the cluster held together. Some unseen mass had to be providing additional gravity. Decades later, in the 1970s, an astronomer named Vera Rubin made similar discoveries by studying the rotation of individual galaxies. Rubin found that the outer regions of galaxies, including our own, were rotating much faster than they should have been if only the visible matter were holding them together. Again, dark matter offered the explanation. Today, the existence of dark matter is supported by many independent lines of evidence. The motions of stars in galaxies, the gravitational lensing of distant light, the patterns of the cosmic microwave background, all of them point to a universe in which dark matter outweighs ordinary matter by about 5 to 1. Dark matter is real, even if we cannot see it. And yet, despite all this evidence, we do not know what dark matter is made of. Many theories have been proposed. It might be made of unknown subatomic particles called WIMPs, weakly interacting massive particles. It might be made of axions, even lighter and more elusive particles. It might be primordial black holes formed in the very early universe, or it might be something stranger still. Astronomers and physicists are searching very patiently for dark matter. Underground laboratories are looking for the rare instances when a dark matter particle might collide with an ordinary atom. Particle colliders are trying to produce dark matter particles directly. Telescopes are watching for the indirect signatures of dark matter annihilation in the centers of galaxies. So far, no dark matter particle has ever been directly detected. The mystery has only deepened with each careful search. Whatever dark matter is, it is good at hiding. It interacts with ordinary matter only through gravity, and perhaps through some other extraordinarily weak force we have not yet discovered. In the meantime, dark matter shapes the Milky Way in deep, important ways. The vast invisible halo of dark matter is what holds the disk of our galaxy together. Without it, the outer stars and gas would not move in their observed orbits. The Milky Way as we see it tonight would not exist if dark matter did not exist. Astronomers think the Milky Way's dark matter halo extends out to perhaps 250,000 light-years from the Galactic Center. That is more than twice the diameter of the visible disk. In every direction we look outward from the center, the dark matter halo continues, slowly fading with distance. The total mass of the Milky Way's dark matter halo is roughly 1 trillion solar masses. That is several times more mass than all the visible stars and gas combined. Most of our galaxy's substance is invisible to our eyes and our instruments, quietly providing the gravity that shapes our home. Within the halo, dark matter is not perfectly smooth. Computer simulations show that it forms clumps and substructures, small concentrations of dark matter that drift through the larger halo. Some of these clumps may host the smallest dwarf galaxies, the faint companions of the Milky Way that orbit slowly through the halo. Indeed, the Milky Way is surrounded by dozens of small dwarf galaxies: the Sagittarius dwarf, the Canis Major dwarf, the various Magellanic objects, and many others. Some of these are slowly being torn apart by the gravity of the larger Milky Way. Their stars stretched into long, graceful tidal streams across the halo. Astronomers have discovered many such tidal streams in recent years, threading through the Milky Way's halo like long, quiet rivers of stars. Each stream is the slowly dispersing remains of a small galaxy that wandered too close to ours. The streams are evidence that the Milky Way has been quietly absorbing smaller neighbors for billions of years. Tonight, somewhere in the dark cosmic halo, particles of dark matter are drifting slowly through space, unobserved but exerting their gentle gravitational pull. Tonight, somewhere in the halo, ancient stars older than the Earth itself are slowly orbiting through the deep, dark, cosmic envelope of our galaxy. The halo continues, peacefully, exactly as it has for ages. Let us drift very gently into one of the most beautiful regions of the halo, the ancient globular clusters that scatter through it like patient gathered crowds. Scattered through the halo of the Milky Way are some of the oldest and most beautiful structures in our galaxy. The globular clusters. Each is a dense, roughly spherical ball of stars, sometimes containing hundreds of thousands or even millions of ancient stars, all bound together by gravity. Tonight we will visit them gently. There are about 150 known globular clusters in the Milky Way, though some astronomers think more remain to be discovered, hidden behind the dust of the galactic disk. Each one is a self-contained little system, orbiting slowly through the halo on its own long elliptical path that takes it far above and below the plane of the galaxy. Globular clusters are extremely old. Most of them formed about 12 to 13 billion years ago in the very early universe, soon after the Milky Way itself began to coalesce. The stars in a globular cluster are some of the oldest stars known. They formed when the universe was younger, smaller, and quieter than it is today. Because globular cluster stars are so ancient, they tell us a great deal about the early history of the universe and the Milky Way. By measuring the ages of these stars, astronomers can put a lower bound on how old our galaxy must be. The oldest globular clusters are at least 12 billion years old, which means the Milky Way must be at least that old too. Looking at a globular cluster through a telescope is one of the great peaceful pleasures of amateur astronomy. The cluster appears as a dense glowing ball of light, packed with countless points of starlight at its center and gradually thinning at its edges. The brightest globular clusters are visible to the unaided eye on dark, clear nights as faint round patches of light. Among the most famous globular clusters is Omega Centauri in the southern constellation Centaurus. Omega Centauri contains about 10 million stars and is the largest known globular cluster in the Milky Way. It is so dense that the stars at its center are only a tenth of a light year apart, much closer than the 4 light years between our Sun and its nearest neighbor. Another famous globular cluster, Messier 13, sits in the constellation Hercules and is one of the most beautiful sights in the northern sky. Through a small telescope, Messier 13 appears as a soft, glowing ball. Through a larger telescope, the individual stars at its outer edges become visible, while the dense core remains a brighter haze of unresolved starlight. Messier 13 lies about 25,000 light-years from Earth. The light we see from it tonight has been traveling for 25,000 years. It left the cluster long before any human civilization existed and arrived at our telescopes during our lifetime. The cluster has been quietly shining all that while. Inside a globular cluster, the night sky would be unlike anything we know on Earth. From a planet near the cluster's center, hundreds of bright stars would fill the sky in every direction, brighter than the full moon, with no patches of true darkness. The night sky would never truly be dark anywhere. Globular cluster stars are mostly old, Low-mass stars, red dwarfs and subgiants, and white dwarfs in late stages of their lives. Massive stars in the cluster long ago burned through their fuel and went supernova, scattering their remnants. The clusters today are populated mostly by patient, long-lived stars that have been quietly fusing for billions of years. Globular clusters are bound together by their own gravity. The stars in a cluster orbit the center of mass of the cluster in slow loops that take many millions of years to complete. The cluster itself orbits the center of the Milky Way on a much larger scale, taking hundreds of millions of years per orbit. Some globular clusters orbit so close to the galactic disk that they have lost stars over time, stripped away by the gravitational tidal forces of the Milky Way. We can see long, thin streams of cluster stars extending behind these losing clusters, like the gentle wakes of cosmic boats moving through a deeper darkness. Among the stars of globular clusters are some of the most metal-poor stars known. Astronomers use the word metal in a peculiar way to them. Any element heavier than hydrogen or helium is a metal. Globular cluster stars formed when the universe had very few metals available, so they contain almost no carbon, oxygen, iron, or other heavier elements. In the very oldest globular clusters, astronomers have found stars with metallicities thousands of times lower than the Sun. These ancient stars are made almost entirely of hydrogen and helium. They are time capsules from an age when the universe itself contained little else. Among the famous individual stars in globular clusters is HD 140,283, sometimes called the Methuselah star in the constellation Libra. Its age has been estimated at over 13 billion years, almost as old as the universe itself. The star is a slow, patient witness to nearly the entire history of cosmic time. Some globular clusters may not have been born inside the Milky Way at all. They may have been part of small dwarf galaxies that the Milky Way absorbed long ago. The stars are now wandering through the halo of our galaxy, but their origin is older and stranger than that of the Sun and its neighbors. Some clusters are known to host what astronomers call intermediate mass black holes. Black holes thousands of times the mass of the Sun, larger than ordinary stellar black holes, but smaller than the supermassive ones at galaxy centers. These cluster black holes are difficult to confirm, but evidence is slowly accumulating. Inside the densest globular cluster cores, stars sometimes pass close enough to interact gravitationally. Occasionally, two stars merge to form a single more massive star, a process that produces the rare and beautiful blue stragglers, ancient stars that look surprisingly young because they have been refreshed by collision. Tonight, the globular clusters of the Milky Way are still there, where they have been for billions of years. Omega Centauri, Messier 13, the Methuselah star, and all their countless companions are still slowly turning in their dense, crowded ways. The cosmic story of the globular clusters continues peacefully, exactly as it has for ages beyond imagining. Let us drift very gently back into the disk of the Milky Way and visit our own quiet stellar neighborhood, the small region of the galaxy that contains our Sun and its nearby stars. Out in the disk of the Milky Way, Far from the bright central bulge and the dense globular clusters of the halo, our sun drifts quietly through its own little neighborhood. Tonight we will look around at the stars closest to home and consider what they are like. The closest star to the Sun is Proxima Centauri, a small red dwarf about 4.2 light-years away. Light from Proxima takes 4 years and a few months to reach us. The star is so dim that it cannot be seen with the unaided eye, even though it is the nearest of all the stars to home. Proxima Centauri is part of a triple star system, together with 2 larger Sun-like stars called Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is slightly larger and brighter than the Sun. Alpha Centauri B is slightly smaller and dimmer. Together, the 3 stars form a quiet gravitational dance 4 light-years from us. From Earth, Alpha Centauri A and B together appear as a single bright point in the southern sky, in the constellation Centaurus. They are the 3rd brightest star in the night sky, after Sirius and Canopus. To people who live in the southern hemisphere, Alpha Centauri is one of the familiar bright lights of the heavens. In 2016, astronomers discovered a planet around Proxima Centauri, Proxima b, an Earth-sized world orbiting in the habitable zone where liquid water could potentially exist. Whether life could survive there is uncertain, but the discovery was a quiet reminder that the nearest star to the Sun has its own family of worlds. Beyond the Alpha Centauri system, the next nearest star is Barnard's star, about 6 light-years from us. Barnard's star is a small red dwarf, even smaller than Proxima, and it is one of the fastest-moving stars in our sky, drifting across the constellation Ophiuchus at a noticeable rate over the course of a human lifetime. Then comes the Wolf 359 system, just under 8 light-years away, another small red dwarf, and Lalande 21185, another red dwarf at 8 light-years. The pattern repeats. Most of our closest neighbors are small, dim red dwarfs, the most common stars in the galaxy. Among the closer stars, there are also a few brighter ones. Sirius, the brightest star in our night sky, is about 8.6 light-years from us. Sirius is actually a binary system, a bright main star, and a faint white dwarf companion called Sirius B, locked in a slow 8-year orbit. Sirius shines so brightly because it is intrinsically more luminous than the Sun, and because it is relatively close. Many other bright stars in our sky are actually much further away, some hundreds or thousands of light-years away, but they appear bright because they are intrinsically much more powerful than the Sun. Within about 33 light-years of the Sun, there are roughly 400 known stars. Beyond about 33 light-years, the number rises rapidly. Within about 1,000 light-years, there are millions of stars. The Sun is in a quiet but not lonely part of the galactic disk. There are plenty of neighbors just spread across vast distances. Over time, our local neighborhood is slowly changing. Stars drift past each other on their long galactic orbits. Roughly 1 million years from now, several stars currently far away will pass closer to the Sun than Proxima Centauri does today. The neighborhood is constantly being reshuffled on cosmic timescales. In particular, a small star called Gliese 710 is currently about 64 light-years away, but is heading toward the Sun. In about 1.5 million years, it will pass within 16,000 astronomical units of the Sun, close enough to gravitationally disturb the outer Oort cloud of comets surrounding the solar system. Beyond our nearest neighbors, the Sun and its nearby stars all sit within a structure called the local bubble, a roughly bubble-shaped region of the galactic disk where gas density is unusually low, perhaps because of ancient supernova explosions millions of years ago. The Sun has been drifting through this local bubble for the last several million years. Within the local bubble, the Sun also drifts through smaller features: the local interstellar cloud, a small cloud of slightly warmer gas, and the G cloud, a neighboring small cloud. The Sun has been within the local interstellar cloud for about 10,000 years and may exit it in another 20,000 years. The Sun moves at about 220 kilometers per second through the galaxy on its long, slow orbit around the galactic center. From the perspective of the local interstellar medium, the Sun is a slowly moving body, dragging its bubble of solar wind along with it as it goes. That bubble of solar wind, called the heliosphere, extends out to about 120 astronomical units beyond the Sun, well past the orbit of Pluto. Inside the heliosphere, the Sun's wind dominates. Outside, the interstellar medium takes over. The boundary between them is called the heliopause. The Voyager spacecraft, launched from Earth in 1977, have crossed the heliopause and are now drifting in true interstellar space, the first human-made objects to do so. They continue their slow outward journey, carrying their golden records with them, perhaps to be encountered by other beings billions of years from now. Looking out from our local neighborhood, the constellations we see in the night sky are simply the patterns of nearby stars projected onto the cosmic background. Many of the stars in any given constellation are at very different distances from us. They only appear close together because of the angle from which we view them. From the perspective of a planet around a different nearby star, the constellations we know would look completely different. Orion, the Big Dipper, Cassiopeia, all of these familiar shapes are local to our viewpoint. They would not exist for an observer in any other star system, even one only a few light years away. Tonight, the Sun is quietly drifting through its small piece of the galaxy, surrounded by its closest stars, embedded in its local bubble, carrying its planets and its species along on a slow, gentle journey. The cosmic neighborhood continues, peacefully, exactly as it has for billions of years. Let us drift very gently outward to consider the long, slow orbit of the Sun around the entire Milky Way, the great galactic year that we will explore in the next chapter. Just as the Earth orbits the Sun once a year, the Sun itself orbits the center of the Milky Way. But the Sun's orbit is much, much larger than the Earth's. A single trip around the galactic center takes about 230 million years. This vast cosmic period of time is called a galactic year. 230 million years is a remarkable span. The Earth has been around for about 4.5 billion years, which means our planet has completed only about 20 galactic years since it formed 20 laps around the Milky Way. The dinosaurs lived during the previous galactic year. The first life on Earth lived perhaps 30 galactic years before that. The Sun moves through the galaxy at about 220 kilometers per second relative to the galactic center. That sounds fast, and it is by everyday standards, but the orbit is so vast that even at that speed, a single lap takes more than 200 million years to complete. In a single human lifetime, say 80 years, the Sun moves about 550,000 million kilometers along its orbit. That sounds like an enormous distance, and it is, but on the scale of the galaxy itself, it is an utterly insignificant fraction of a single lap. We are barely moving at all in cosmic terms. The orbit of the Sun is not a perfect circle. It is slightly elliptical, and it also wobbles up and down across the plane of the galaxy as the Sun bobs gently above and below the disk. The Sun rises above the disk for about 30 million years, then sinks back below it, then rises again. We are currently slightly above the galactic plane. Each time the Sun passes through the galactic plane, it can encounter denser regions of gas and dust. Some scientists have speculated that these encounters may correlate with mass extinction events in Earth's history, as gravitational disturbances from passing matter could destabilize the Oort cloud and send more comets toward the inner solar system. This is still a debated idea. The patterns of mass extinctions on Earth do not perfectly align with the Sun's galactic motion, but the broader principle that our planet's history is somehow connected to our galactic motion is itself a beautiful idea, even if the details remain uncertain. We are part of the larger cosmic story. The Sun's orbit is roughly 26,000 light-years from the galactic center. This means the Sun sits about halfway out from the center to the edge of the visible galactic disk. We are not in the middle of the galaxy, and we are not on the far edge. We are in a comfortable middle region, neither too crowded nor too lonely. Throughout the previous galactic year, the most recent 230 million years of Earth's history, the entire dinosaur era unfolded. 230 million years ago, the early dinosaurs were just beginning to appear. By 66 million years ago, when an asteroid ended the dinosaur age, the Sun had completed about 3/4 of its lap. 2 galactic years ago, in the late Permian, the largest mass extinction in Earth's history occurred. 3 galactic years ago, the early reptiles were emerging. 4 galactic years ago, the first land animals were leaving the seas. Each galactic year encompasses a vast slice of biological history. Looking forward, the next galactic year will end about 230 million years from now. By then, the continents of Earth will have rearranged themselves into new configurations. New species will have evolved and gone extinct. Whatever is happening on Earth then will be unimaginable from our present perspective. The galactic clock will simply have ticked one more time. Within the Sun's galactic orbit, the solar system itself has slowly evolved. 4.5 billion years ago, the Sun and its planets formed from a collapsing cloud of gas and dust. Since then, the Sun has completed about 20 galactic years. The orbit of the Sun has remained relatively stable across all that time, though it slowly precesses and changes. In about 5 billion years, when the Sun reaches the end of its main sequence life and becomes a red giant, it will have completed about 42 galactic years total. That's a great long span, but in cosmic terms, just 42 slow laps around the great cosmic wheel. Other stars in the galaxy have their own galactic orbits. Some are on smaller orbits closer to the center, completing their galactic years more quickly. Others are on huge orbits in the outer disk, taking far longer to complete a single lap. Still others in the halo are on long elliptical orbits that take them far above and below the disk in slow, patient swings. From the perspective of the galactic center, the entire Milky Way disk is slowly turning. Like a great record player rotating very slowly, the disk completes about half a turn during the sun's lifetime. We are participants in that great slow rotation, even if we cannot perceive any of it on the timescales of our own lives. If we could speed up time by 1 billion times, we could watch the galactic year unfold in less than 1/4 of a second. We would see the sun rapidly tracing out its long elliptical orbit, bobbing slightly up and down, sweeping past spiral arms and inter-arm gaps. The galaxy would seem alive with motion, but at our normal pace of life, none of this is visible at all. Tonight the sun is somewhere along its current galactic year. We do not know exactly where, we do not need to know. We are simply continuing the slow journey as we have for billions of years, with the planets in their tighter orbits around us and the entire solar system drifting along on the great galactic wheel. It is humbling but also reassuring to think about the galactic year. It reminds us that our own concerns, our days, our weeks, our years, are nestled within much larger and slower cosmic rhythms. The Milky Way does not notice us, but it also patiently carries us along, exactly as it has done for the lifetime of every creature that has ever lived on Earth. Tonight, the galactic year is still slowly turning. The sun is still on its long lap. The disk is still rotating. The orbit continues peacefully, exactly as it has for the lifetime of the Earth, and exactly as it will continue for billions of years to come. Let us drift very gently beyond the Milky Way itself toward our great spiral neighbor, the Andromeda Galaxy, slowly approaching us across the deeper darkness of intergalactic space. The Milky Way is not alone in the deeper darkness, just 2.5 million light-years away. Our great spiral neighbor, the Andromeda Galaxy, is slowly approaching us across the void of intergalactic space. Tonight we will think gently about that approach. The Andromeda Galaxy is very similar to the Milky Way. It is a large spiral galaxy with several 100 billion stars, a central black hole at its core, vast spiral arms threaded with nebulae, and an extensive halo of dark matter. The two galaxies are like cosmic siblings, sharing the same fundamental architecture. Andromeda is somewhat larger than the Milky Way, containing perhaps 1 trillion stars compared to our 200 billion. It is also somewhat brighter and somewhat more extended. From a great distance, an observer would see Andromeda as the slightly more imposing of the two galaxies. Andromeda is the most distant object visible to the unaided human eye. On a dark, clear autumn night, in the constellation that bears its name, you can see Andromeda as a faint, elongated patch of light. The light reaching your eyes left the galaxy 2.5 million years ago. The first humans were just starting to evolve when that light began its journey. To see the Andromeda Galaxy is to see deep into the past. The light reaching your eyes shows Andromeda as it was 2.5 million years ago, long before the first hominids learned to make fire, long before any civilization existed, long before written history began. Tonight you can see across that vast, quiet stretch of cosmic time. Andromeda is currently moving toward the Milky Way at about 100 kilometers per second. That is fairly fast in cosmic terms, but the distance between the two galaxies is so vast that even at that speed, it will take about 4 billion years for the two galaxies to meet. In about 4 billion years, the two galaxies will begin to merge. The merger will not happen all at once. It will be a slow, gradual process spanning hundreds of millions of years. The two great spirals will pass through each other, gravitationally distort each other, and eventually settle into a single new combined galaxy. Astronomers sometimes call this future combined galaxy Milkomeda, a portmanteau of Milky Way and Andromeda. Milkomeda will be a giant elliptical galaxy, no longer with distinct spiral arms, but instead a great quiet ball of stars on long mixed orbits, settled together after the cosmic dance has finished. During the merger, the two central black holes, Sagittarius A from the Milky Way and the larger central black hole of Andromeda, will eventually spiral together and merge into a single, more massive black hole. This collision of central black holes will release enormous gravitational waves that ripple gently across the universe. Despite the dramatic-sounding nature of a galactic merger, very few stars actually collide during the process. The galaxies are mostly empty space. The Sun and the Earth, 4 billion years from now, will most likely simply drift through the merger without ever meeting another star directly. The merger is gentler than it sounds. However, the merger will dramatically change the night sky as seen from Earth. As Andromeda approaches, it will grow larger and brighter in our sky. By the time the merger is well underway, Andromeda will fill a large portion of the night sky, perhaps as much as 10 degrees across, 20 times the apparent size of the full moon. By the time the merger is complete, the Sun will likely be near the end of its main sequence life. In about 5 billion years, the Sun will swell into a red giant, regardless of what is happening on the cosmic scale around it. The Sun's own quiet ending and the great galactic merger will happen on roughly the same timescale. The Earth by then will have long passed beyond habitability. The slow, steady warming of the Sun across billions of years will have ended life on our planet long before the merger reaches its peak. The merger will be witnessed only by the rocks and dust that remain of our world, drifting silently through the great galactic gathering. Of course, this is all far in the future. 4 billion years is twice the age of multicellular life on Earth. It is hard to imagine in any meaningful way. Nothing about our daily lives or even our human civilization will be present to see the great merger, but the cosmic events have already been set in motion. They are unfolding now very slowly while we sleep. In the meantime, Andromeda is right where it has been for billions of years, visible in the autumn sky as a faint, elongated patch of light. Its light has been traveling for 2.5 million years. The journey began long before there were eyes on Earth to receive it, and will end tonight in the eyes of countless quiet observers across the world. Andromeda is also slowly approaching us in another way. Even when we cannot see it with our own eyes, our radio telescopes and our infrared instruments are continually receiving signals from the galaxy. Astronomers have been studying Andromeda for decades, mapping its stars, its dust lanes, its globular clusters, its central black hole. Some of the most beautiful images of any galaxy in the universe are of the Andromeda Galaxy, photographed in fine detail by the Hubble and other telescopes. We can see individual stars in Andromeda, individual stellar nurseries, individual dust lanes. The galaxy 2.5 million light-years away has become one of the best-studied objects in the universe. Andromeda is also part of a smaller family of galaxies, the Local Group, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. We will visit the Local Group as a whole in the next chapter. For now, it is enough to know that we are not alone in the cosmic neighborhood. Tonight, somewhere across the deeper darkness, Andromeda is still moving toward us. Our telescopes are still receiving its light. The light from Andromeda that arrives tonight on Earth has been traveling since long before the human species existed, on a slow, patient cosmic journey, finally completing its trip in this quiet moment. Let us drift very gently outward to consider the wider family of galaxies that surrounds us, the Local Group of galaxies, scattered through the deeper darkness of the cosmic neighborhood. Beyond the Milky Way and Andromeda, in a region of space about 10 million light-years across, sits the family of galaxies we call the Local Group. About 50 galaxies are part of this family, ranging from the two great spirals down to small dwarf galaxies. Tonight, we will visit them gently one by one. The Milky Way is one of the two largest members of the Local Group. Andromeda is the other, slightly larger than us. Together, the two great spirals dominate the gravitational landscape of the Local Group, and most of the smaller galaxies orbit one or the other. The third largest galaxy in the Local Group is the Triangulum Galaxy, also called Messier 33. Triangulum is a smaller spiral galaxy with about 40 billion stars, perhaps a fifth the size of the Milky Way. It sits about 3 million light-years from us, in the constellation that bears its name. Triangulum is gravitationally connected to Andromeda, and the two galaxies will likely interact during the great future merger. Some astronomers think Triangulum may eventually merge into the combined Andromeda Galaxy as well, becoming part of the larger combined cosmic neighborhood. Around the Milky Way are dozens of small dwarf galaxies. The two largest are the Large Magellanic Cloud and the Small Magellanic Cloud, both visible from the southern hemisphere as faint patches of light in the night sky. The Magellanic Clouds are about 170,000 and 200,000 light-years from us, respectively. The Magellanic Clouds were named after Ferdinand Magellan, the explorer whose crew first described them to European audiences during their voyage around the world in the early 1500s. To people in the southern hemisphere, the Magellanic Clouds had been familiar landmarks of the night sky for thousands of years before that. Inside the Large Magellanic Cloud sits one of the most spectacular stellar nurseries in the Local Group, the Tarantula Nebula. The tarantula is so large that if it were placed at the distance of the Orion Nebula, it would cover 30 degrees of the night sky and cast shadows on the ground. Tonight it sits much further away, glowing softly in the south. In 1987, a star inside the Large Magellanic Cloud went supernova. The explosion was visible to the unaided eye from Earth, the closest supernova to be observed in modern times. Even today, the gentle expanding shell of the supernova remnant is still slowly spreading outward, glowing softly in the southern sky. Beyond the Magellanic Clouds, dozens of smaller dwarf galaxies orbit the Milky Way. Many of these are tiny, containing only millions or even thousands of stars instead of billions. They are faint, ancient, and slowly being torn apart by the gravity of the larger Milky Way they orbit. Among these dwarf galaxies are the Sagittarius dwarf, the Canis Major dwarf, the Sculptor dwarf, the Fornax dwarf, and many others. Each is its own quiet ancient gathering of stars drifting in slow elliptical orbit around the Milky Way center, slowly losing stars to the larger galaxy that holds them in its embrace. Andromeda has its own family of dwarf companions, just as we do. The Andromeda system has roughly 30 known small dwarf galaxies orbiting it, including some quite famous ones like Messier 32 and Messier 110. From our distance, these small companions appear as faint smudges around the brighter Andromeda Galaxy itself. Beyond the Magellanic System and the Andromeda System, there are also some isolated dwarf galaxies in the local group that don't orbit either of the great spirals. The Pegasus dwarf, for example, drifts independently. The IC10 galaxy is another quiet member with its own gravity. Each one is a small, slow cosmic story of its own. The local group has been slowly gathering its members together for billions of years. The galaxies inside it are gravitationally bound. They will not be carried apart by the expansion of the universe. They are, in this sense, our cosmic family. Even as the universe expands and other galaxy clusters drift further away, the local group will remain together for as long as gravity allows. Far in the future, after the Milky Way and Andromeda have merged into Milkomeda, the smaller dwarf galaxies will likely also merge with the combined giant. Over hundreds of billions of years, the local group will probably consolidate into a single, very large elliptical galaxy. The cosmic family will become a cosmic union. The total mass of the local group is roughly 2 trillion solar masses. About 85% of that mass is dark matter, distributed in vast invisible halos around each of the galaxies. The local group is, in a real sense, mostly dark, held together by an unseen substance whose nature we still do not fully understand. Looking outward from the local group, we find that we are not in a particularly exceptional cosmic neighborhood. There are many similar small groups of galaxies scattered throughout the universe. Some are larger, with hundreds of galaxies and a much greater total mass. Some are smaller, with only a few members. The local group is comfortably middle of the road in cosmic terms. Beyond the local group, the next nearest collection of galaxies is the Maffei group, only about 10 million light-years away, and the Sculptor group a similar distance off. Beyond these, the Great Virgo cluster, with over 1,000 galaxies, dominates the sky at about 50 million light-years from us. The local group itself is a small outer member of the Virgo supercluster, an even larger structure containing thousands of galaxies, and the Virgo supercluster is a small part of the Laniakea supercluster, an extraordinarily vast collection of structures spanning over 500 million light-years. The Milky Way is nested within nested cosmic structures of ever larger scale. Tonight, the local group is still gathered together where it has been for billions of years. The Magellanic Clouds are still drifting around our galaxy. The dwarf galaxies are still being slowly torn apart. Andromeda is still approaching. Triangulum is still glowing softly in the constellation that bears its name. The whole quiet cosmic family is still drifting together through the deeper darkness. Let us drift very gently outward one final time to place our home galaxy within the very largest structures of the universe, the cosmic web of clusters, filaments, and voids that fills the universe at its grandest scale. At the very largest scales we have ever observed, the universe is not uniform. Galaxies are not scattered randomly through space. Instead, they are gathered into a vast network of long filaments, dense clusters, and great empty voids, a structure astronomers call the cosmic web. Tonight we will look gently at our home galaxy within this grandest of cosmic landscape. In the cosmic web, galaxies cluster along long, thin filaments, strings of galaxies stretching across hundreds of millions of light years. Where filaments meet, they form denser clusters of galaxies, the great cosmic intersections. Between filaments, there are vast empty regions, voids, where almost no galaxies exist. Our local cosmic neighborhood is part of one of these filaments. The Milky Way, the local group, the Virgo cluster, and many other nearby structures are all strung along a great cosmic filament that astronomers have named the Laniakea supercluster. We are nested within nested structures, all of them held together by gravity. Within Laniakea, our motion is influenced by an enormous gravitational attractor that astronomers call the Great Attractor, a region of unusually high mass density about 200 million light-years from us. The local group is slowly being pulled toward the Great Attractor at about 600 kilometers per second. Beyond the Great Attractor sits something even larger, the Shapley supercluster, the most massive concentration of galaxies in our cosmic neighborhood, 600 million light-years away. The Shapley supercluster contains tens of thousands of galaxies and is influencing the motion of our entire local region. Despite the gravitational attractions of these distant cosmic structures, the universe as a whole is expanding. Galaxies that are not gravitationally bound to us are moving away, carried by the expansion of space itself. The expansion is accelerating, driven by what cosmologists call dark energy, a mysterious force that fills empty space and pushes galaxies apart. Dark energy makes up about 68% of the energy content of the universe. Dark matter accounts for another 27%. Ordinary matter, the stuff that stars, planets, and people are made of, is only about 5% of the total. The Milky Way is part of a small minority of the universe's contents. The cosmic web took billions of years to form. In the very early universe, all matter was distributed almost uniformly. Tiny variations in density, however, slowly grew under gravity. Denser regions pulled in more material. Less dense regions emptied out further over billions of years. The structure we see today gradually emerged. Computer simulations of the cosmic web, running on the largest supercomputers, show how the patterns formed. The simulations begin with the conditions of the very early universe and run forward in cosmic time. The result, after billions of simulated years, is a cosmic web remarkably similar to the one we observe in the actual universe. Our position in the cosmic web is fairly ordinary. We sit in a moderately dense filament, far from any major cluster center, in a quiet outer region of the Laniakea supercluster. We are not at the center of anything cosmologically significant. The Milky Way is one of perhaps 200 billion galaxies in the observable universe. 200 billion galaxies, each containing perhaps 100 billion stars on average, each star with its own potential for planets. The total number of stars in the observable universe is somewhere around 2 times 10 to the 22nd power, a 2 followed by 22 zeros. The number is unimaginable. And yet, despite all those galaxies and all those stars, the universe is mostly empty. The cosmic voids, the great empty regions between filaments, make up most of the volume of the universe. Galaxies, even gathered in clusters and filaments, occupy only a small fraction of the available space. The cosmos is largely a vast, quiet emptiness. Some of the cosmic voids are extraordinarily large. The Bootis void, for example, is about 330 million light-years across. Inside it, there are very few galaxies to live inside. Such a void would be to look out at a sky almost empty of distant lights, with neighbors so far away as to be nearly invisible. Tonight, we are not in a void. We are inside a galaxy, in a small group, on a filament of the cosmic web. We have neighbors: Andromeda, Triangulum, the Magellanic Clouds, the local group, the Virgo cluster. We are not alone, even at the largest scales of cosmic structure. Looking back across all that we have seen tonight, the Milky Way's spiral arms, its central black hole, its ancient halo, its dwarf companions, its slow approach to Andromeda, and now its place in the cosmic web, we have moved gently outward across many scales of cosmic structure, from the Sun's neighborhood to the largest patterns visible in the universe. Throughout that vast cosmic landscape, the Milky Way is one quiet, small place, but a place that contains us, our planet, our species, our consciousness, our cells, our breath. Inside this great cosmic structure, we exist tonight on a small drifting world with all the long quiet history of the cosmos folded into it. The cosmic web continues to evolve. Galaxies still move along filaments. Clusters still grow as galaxies fall into them. Voids still slowly expand as space itself expands. The patterns of the cosmos are not static. They are slow-moving rivers of structure flowing through deep cosmic time. Eventually, in the far future, the accelerating expansion of the universe will carry distant clusters out of our cosmic horizon. The galaxies in our own gravitationally bound region will remain together. The local group will stay intact, but everything beyond it will slowly drift away into the dark. Our cosmic neighborhood will become an isolated island in an expanding sea of darkness. Tonight we are not yet at that far future. The cosmic web is still rich with distant galaxies. We can still see Andromeda, the Virgo cluster, the more distant superclusters. Our cosmic neighborhood is full of company. The vast quiet cosmos continues peacefully exactly as it has for nearly 14 billion years. And tonight, somewhere within all of this great cosmic structure, the Milky Way galaxy is still slowly turning. Its 200 billion stars are still on their long, quiet orbits. Its central black hole is still the patient anchor of the great wheel. The cosmic story of our home galaxy continues, peacefully, exactly as it has for ages beyond our imagining. Let us drift very gently back from the largest scales of the cosmos toward the simple comfort of your own room, toward the soft farewell that ends our long cosmic journey for the night. And so we begin to drift back very gently from the cosmic distances we have traveled tonight, from the vast spiral arms, the ancient globular clusters, the patient central black hole, the slow approach of Andromeda, back toward the simple quiet of your own room, your own bed, your own slow breath. The Milky Way is still turning quietly above you. The 200 billion stars are still on their long, slow orbits. The galactic year is still being slowly measured out, 1/4 billion years at a time. None of that requires anything from you tonight. The galaxy has been continuing for billions of years without your help, and it will continue tonight while you rest. Thank you for spending this night with the Circadian Institute. If this journey helped you rest, please consider subscribing. It allows us to keep building these slow, deep visits to the quieter places of the cosmic world of the Milky Way galaxy. New videos arrive each week, always at this same patient pace, always meant for your sleep. Good night. Outside this video, the night is still going. The 200 billion stars are still turning quietly together, each on its own slow orbit around the Galactic Center. The ancient globular clusters are still drifting in the galactic halo, their patient stars older than the sun itself. The spiral arms are still slowly winding through the disk of the galaxy, exactly as they have for billions of years. Tomorrow comes when it comes. Until then, sleep deeply. Good night from the Circadian Institute. Good night from the Milky Way galaxy. Good night from the spiral arms, the ancient stars, the quiet central black hole, the slow approaching Andromeda. The cosmic story will continue patiently, exactly as it has for nearly 14 billion years. Sleep deeply, and we will meet again tomorrow.